Welcome to everybody. This is the third seminar of the series organized by CIDE. I don't think Enrico needs a long presentation actually, because he's a well-established scholar in the macroeconometric field. He's currently professor of econometrics at the Department of Economics and Management of the University of Padova. And he's also a senior research fellow at Fondazione Bruno Kessler, IRVAP, who is a research institute for the evaluation of public policies. Enrico's research interest is very wide, because it covers many fields of econometrics, ranging from methodological aspects of policy evaluation up to more applied research in labor economics. So we can consider Enrico as a researcher able to answer difficult questions related to real life using rigorous statistical methodologies. His research has always been at the frontier of the knowledge, and for this reason he has published in top leading journals like American Economic Review, Review of Economic Studies, Journal of Econometrics, Journal of Royal Statistical Society. And last but not least, he also writes many good scholars like Eric Battistin, for example, who is at the University of Maryland, but many others actually can claim that they were Enrico's students. So I think that it's better I stop talking and I leave the floor to Enrico presenting this paper on the perils of normalizing and pooling in RD designs. Enrico has approximately 45 minutes. You can ask questions, writing questions. You can write questions during the presentation if there are short questions or clarification questions. If there are deeper questions, we have 15 minutes at the end of the presentation. Okay, the floor is yours, Enrico.
Thanks, Daniela. Thanks, Gabriele, for inviting me to give this talk. So this is about regression discontinuity design, and particularly in the case in which we have several different rankings. So think of a program delivered in a number of different sites. In each site, the assignment to the treatment, the intervention, is based on the RDD protocol, and then you put together those different sites. And there are a number of problems arising in this instance we are. So let me, first of all, remember there are co-authors of mine in this paper, Margherita Forte, Andrea Icchino, and by the way, this is a spin-off project of their paper in the Journal of Political Economy. I'm saying something on that paper. Okay, so let me start from reviewing very briefly what the regression discontinuity design is. So there are individuals in a target population. They are either exposed or unexposed to an intervention. The capital D is the binary variable for this exposure status. 1 for those in, 0 for those out. We want to measure the average causal effect of this intervention, being exposed to the intervention with respect to an outcome Y. We have available a sample of individuals from the target population. So I'm using, of course, the usual potential outcome notation to describe the variables of this evaluation problem. So Y1 and Y0 are the potential outcomes for a specific individual in the population in case that individual is exposed, not exposed to the intervention. The outcome we do observe, Y, without suffix, is either Y0 or Y1, depending on whether that individual is in or out of exposure to the intervention. The RDD selection rule. So to decide who is in and who is out, according to the RDD protocol, individuals are ranked according to the values of a continuous observable variable X. This is named very often running variable in the terminology of the RDD. And X is predetermined to the intervention. So it is a continuous observable characteristics of individuals determined before the beginning of the intervention. function. So fx is the regular probability density function of this random variable x. So the exposure status is determined according to this rule. So whether or not x, the random variable, is above or below c. C is the cutoff. It is a point in the support of x, and it is established in advance. This is the typical case for the RDD. So there are a long list of examples in the empirical literature, but think of the case of incentives to students awarded on the basis of an observed test score, or a training program mandatory for individuals with more than a pre-specified number of months in unemployment. So we call this rule allocation rule 1. So remember, C cutoff point established in advance. How do we proceed to estimate the average causal effect? So to the left of the cutoff, C, a left neighborhood of the cutoff, we evaluate the average outcome for individuals to the left of C, those not exposed to the intervention, untreated if you want. And of course, on them, we observe the average outcome Y0, the average outcome under non-exposure. Epsilon here is a small positive number. I mean, it is I'm defining the left neighborhood here. And to the right of the cutoff, the right neighborhood again, what we observe is the average value of Y1, the potential outcome under exposure, which is equal to the potential outcome without exposure plus the average causal effect immediately to the right of the cutoff. If we take the difference between 3 and 2, so we compare the average outcome for individuals immediately to the right, immediately to the left, we end up with this expression here. And here is the role of the identifying restriction of the RDD. So what we claim to identify this average causal effect here is that the regression of Y0 on X, the regression of the potential outcome under no treatment on the random variable, is a continuous variable of the random variable, a continuous function of the random variable at the cutoff. So the second term here, the second line of equation 4, due to this continuity restriction, is equal to 0. So this way, by contrasting the average outcome for those immediately above to the average outcome for those immediately below, we end up with the average causal effect for individuals at the cutoff. It is a local average causal effect for a very specific subpopulation, individuals close to the cutoff. So the intuition behind the identifying restriction of the RDD, the continuity of this regression, is very simple. So the difference in 4 here, it deserves a causal interpretation if in the absence of the intervention, there would be no discontinuity at the cutoff. So the intervention is the only thing happening exactly at the cutoff. In the absence of the intervention, nothing strange would happen at the cutoff. So to implement this idea, to take it to the data, what we do in practice is very simple. We run the regression of the outcome on the random variable, Y on X, separately to the right and to the left of the cutoff. And then we measure the jump, the difference between the two regressions, exactly at the cutoff. That jump, if any, is the average causal effect on that specific subpopulation. This is typically done using non-parametric methods. So, for instance, the local linear regression. And there are rules, I'm not going to the details here, of course, rules to select the optimal bandwidth, let's say, the size of the neighborhood around the cutoff. You need to define those immediately above and those immediately below the cutoff. Okay. The multi-cutoff case, the case we discussed in this paper, is so think of the intervention being implemented in capital J different sites. And in each site, individuals are ranked on the random variable, separately in each site. And the cutoff CJ, in principle, is varying across sites. So the motivating example is the paper by Margherita, Andrea, and Giulio, Journal of Political Economy. And what they estimate there is the cognitive and non-cognitive costs of daycare for children in 0 to age bracket. So what they do in the paper is to pull together the data from a number of different kindergartens in Bologna. And in each kindergarten, the assignment to the intervention is admission to the kindergarten. Takes place according to the RDD protocol. And they pull together the data from these capital J different rankings. Okay, so this is the motivating example by the way, this paper is spin-off of that. So there is nothing new if the sample size is enough large for an analysis side by side. So if the number of applicants is large in each site, what you do is to run an RDD in each site separately. So you apply the standard RDD. The problem is when the sample size is small, when the number of applicants per site is too small to obtain a reliable estimate at the site level. So in that case, all you can do is to content yourself with a kind of a cross-site average causal effect. You give up estimating the causal effect at the site level and estimate an average across sites. You pull together the data across sites. So the normalizing and pooling estimator, NP, is very simple. What you do is you normalize the running variable by taking the difference between X and the site-specific cutoff CJ. So this way you have a cutoff, a common cutoff at 0 across all the sites. And then you put together the capital J sites and go ahead with the standard RDD using the normalized random variable, of course, as if it were a standard RDD. Okay. The case we analyze in this paper, we name it allocation rule 2, is the following. So it is not the cutoff to be set in advance. What you set in advance is the number of available slots. You decide before starting your experiment, in this site, there will be capital K, J slots, capital K, J participants, and NJ minus KJ non-participants. There are NJ applicants in site J, and you fill in the available slots, starting from the highest score applicant, the highest value of the running variable X, until exhaustion of the available slots in that site. So the cutoff CJ in this site ex post coincides with the score of the marginal unit exposed to the intervention. Okay. So the difference between allocation rule 1 and allocation rule 2 is under allocation rule 1, you set in advance the value of the cutoff. Under allocation rule 2, you set in advance the number of individuals exposed to the intervention in each site. And what we show in the paper is that the NP estimator, the normalizing and pooling estimator, might fail in this setup. It is might be biased. Even take care, even if the continuity condition, the RDD continuity condition, holds separately in each site. Okay. So we ran a very survey across journals to understand how much this problem is spread in empirical work, and we found 24 papers in economics, political science, published since 2007, falling into this setup. Of course, there might be something else we are not able to find out. And here is the list of papers we found. Oh, so let me draw an analogy to the randomized control trial to make the main point we want to make with this paper. So if the RDD identifying restriction holds, that is, if the exposure status of units depends only on the sign of the difference between X and the cutoff, so it is as if in the vicinity of the cutoff an RCT took place. It is as if you were randomly assigned the treatment, the intervention, to individuals close to the cutoff. There is an ancient paper by White and Campbell, published in 1960. And in this paper, they made this point. Remember, the RDD is essentially a local RCT. And this is, of course, the strength of the RDD, the reason why it is so popular in the empirical research. Then, if the intervention is implemented in capital J different sites, the case we are considering, and in each site the assignment follows the RDD protocol, it is as if it were a stratified RCT. Each site is a stratum, and within the stratum, the exposure status is randomly determined, locally at the cutoff, of course. So if Cj is determined in advance, our allocation rule 1, the expected number of units in a neighborhood of the cutoff is proportional to Nj Fj. Nj is the total number of applicants. Fj is the density of the running variable at the cutoff. Okay, so the expected number of units is proportional to Nj Fj, both to the right and to the left of the cutoff. So the expected number is exactly the same for participants and non-participants. The straightforward implication is that the probability of exposure, remember, under allocation rule 1, the probability of exposure at the cutoff is 0.5, exactly. And there is no variability across site in this probability of exposure. Then what you do is very simple. You take your regression, you pull together all the data, all the strata, all the sites, and run the regression of the outcome on the treatment status, restricting the sample to units close to the cutoff. And this way you identify the average cause effect as if it were an RCT. Okay. Okay, note that as far as you are concerned about identification of the causal parameter beta, there is no need to include site fixed effect in this regression. Because since the average value of D is exactly the same in all sites, 0.5, there is no room for a correlation between the site fixed effect and the explanatory value. So there is no bias here. So you do not include site fixed effect here to get rid of a non-existent bias. But still, you might want to include site fixed effect to gain precision in the estimate of your causal effect. You end up with a more precise estimate of the causal parameter as far as sites are heterogeneous with respect to the average outcome potential. Okay. So this is exactly the story, the same story for the RCT. When you go with a stratified RCT, you do include in your regression stratum fixed effect to gain precision for your estimate, even if you don't need to include them to obtain an unbiased estimate of your causal parameter. There is an additional comment on the Moulton factor, but I'm skipping it because we are short of time today. Okay, so let's switch to allocation rule 2. When it is the number of slots per site, not the cutoff, to be determined in advance, what we show in the paper is that the probability of exposure, it is no longer 0.5. Okay? And even more important, that probability is varying across sites. It is not the same in all sites. As a consequence, if the site fixed effects are correlated to D, the regression of Y on D is not yielding an unbiased estimate of your causal parameter. This is the bottom line, the problem we deal with. The regression of Y on D, locally at the cutoff, of course, might fail to identify the causal parameter. And the key point is here. The probability of exposure is no longer 0.5. It is varying across sites. So here is a bit of additional ingredients, elements of the problem. So under allocation rule 2, when you set in advance the number of slots, the number of individuals not exposed to the intervention is nj minus kj. Applicants minus number of slots in the site. Then there is one unit exactly at the cutoff, the marginal participant, and kj minus 1 units to the right of the cutoff. Here is the reason why the probability of exposure is no longer equal to 0.5, because the expected number of units in a neighborhood of the cutoff, it is the same as under allocation rule 1 to the left, proportional to nj fj. Remember, nj, number of applicants, fj, the density of the non-invariable. But to the right of the cutoff, it is no longer equal to nj fj. It is this strange number here. Not explaining here why, where this number here comes from, but it is clear that they are different. Okay. So as a result, the probability of exposure at the cutoff is not equal to 0.5, and it varies across sites as a function of kj, nj, fj. Okay. So if the site expect the average potential outcome in site J is correlated to this probability, well, your NP, your normalized and pooled estimator is biased. The standard problem of omitted regression. Oh, there is an additional word of caution about the use of bias, because let me explain this subtle point, the parameter of interest. So under allocation rule 1, there is no ambiguity in the definition of the causal parameter. It is simply the weighted average across sites of the site-specific average causal effect. And the weight of each site is just proportional to the number of units at the cutoff. It's very intuitive. And this is no longer the case under allocation rule 2, because the weight of the sites to the left and to the right of the cutoff are different, as an implication of the probability not being equal to 0.5, the probability of exposure. So to the left of the cutoff, the weight of each site is the same as under allocation rule 1, but to the right of it, it is different. It is this one. So the implication is that under allocation rule 2, there are two different causal parameters. The average treatment effect for those not undergoing the treatment, the AT and T, in the standard terminology, and there is an ATT, the average treatment effect for the treated. And in general, those two causal parameters are not equal. They are equal only if this condition holds here. Remember that W minus W plus under allocation rule 2 are different. They are the weight of the site, J, to the left and to the right of the cutoff. So if this difference here is correlated to the site-specific causal parameter, the two parameters here, AT and T and AT, are different. Okay, so in the following, I'm developing my discussion with reference to the AT and T. But for the case of ATT, it is exactly the same line of reasoning. The ATT, AT&T is often a parameter of interest because it answers the question, what would happen if I marginally expand the intervention? So if I admit to the intervention those marginally excluded to it. To answer this question, you need to identify the average treatment effect on those marginally excluded from the intervention. So the bias for the NP estimator for this causal parameter, the ingredients of the bias are here. So first, the average value across sites, average value of NJFJ, number of units at the cutoff, and this second quantity here, I'm telling you in a moment what exactly this quantity here is. first ingredient. Second ingredient, the degree of a cross-site heterogeneity with respect to the average potential outcome Y1, with respect to the number of units cutoff, and with respect to this second number here, Nj, Fj divided by Qj. And lastly, the correlation between the average potential outcome in the site and those two numbers here. So in particular, the bias of the NP estimator is 0 if at least one of the following conditions hold. So the first condition is, well, simply having a large number of units. So if Nj grows to infinity, the bias disappears. But this is not the case we are focusing on here, because it is clear that if Nj is large, if you have a large number of units in each site, well, you don't really need to pool across site. You run a standard RDB in each site. But here our concern is, what do we do when the number of units per site is small and we must pool data across sites? The second condition here is that either the fixed effect, the site fixed effect, or the average of the explanatory variable does not vary across sites. But in that case, it is clear that the bias is not a problem. The third condition is the standard omitted variable problem. If the omitted variable is unrelated to the explanatory variable, of course, there is no bias. Okay. So here is essentially the core of the reason why there might be a bias. Under allocation rule 2, when you pool data across sites. So the origin of the problem is that when we play with the allocation rule 2, there is one exposed unit exactly at the cutoff, the last participant, the last unit exposed to the intervention. So it is tempting to say, okay, let's throw that guy away. Let's work with a sample without marginal participants. What does it happen in that case? So it is simple to, in the paper we show that in this case, the probability of exposure to the intervention at the cutoff is like this. It's a very simple equation. It is smaller than 0.5. And again, it is varying across sites as a function of Kj. So unless Kj is constant or large, unless those two special cases, again, there is room for a cross-site correlation between the site fixed effect and the explanatory variable. So you do not, in general, you do not get rid of the problem by excluding individuals. I mean, here, I'm running out of time, but a few details here on the bias of the NP estimator. So the point here is, okay, there is a bias, whether or not we keep units at the cutoff. The question, of course, is this bias relevant in practice, or can just think it is negligible? So in case we keep units at the cutoff, the leading term of the bias, when Nj is a small number of applicants, the leading term is this covariance here. It is the covariance between the average potential outcome under exposure and the number of units at the cutoff. So if this covariance is large, the bias is large. And the intuition here is, think, for instance, of an educational context. That covariance is large in absolute value if schools attracting students with the best outcome, an average value of Y1 large, are also more popular. That is, they attract a larger fraction of applicants, both in general and in the neighborhood of the cutoff. So under this condition here, the covariance here will be large and the bias of the NP estimator will be large. So if we discard units at the cutoff, So we avoid having an individual exactly at the cutoff. Things are a bit more tangled up. This is the relationship between the bias in this case and the previous bias, keeping units. You see here that Hj is the quantity I told you before. So it is Fj divided by the ratio Kj to Nj. And this is the hazard function of the running variable at the cutoff. The density at the cutoff divided by the probability of being having a value of the running variable larger than the cutoff. Okay. So the quantity here, it is easy to show that this quantity here is smaller than 1. Okay. But then whether bias 2 is larger or smaller than bias 1, whether you gain or you lose by discarding units at the cutoff, it depends on, there is a ratio here, exactly. It depends on the size and on the sign of these two covariances. In general, you can't say. So it could be both larger and smaller. So you might gain or lose by discard in terms of bias, by discarding units at the cutoff. Okay, so why don't we add site fixed effect to get rid of the problem? So the intuition is straightforward. So if the bias is due to a correlation between the site fixed effect and the explanatory variable, then we control for the site fixed effect. That's it. Okay. So the estimate of the fixed effect estimator is like this. So what you do is to take the contrast at the site level in each site between the average outcome to the right and the average outcome to the left, in the neighborhood, of course, of the cutoff. And then you take the weighted average across sites of that site-specific causal effect. So it is this way you end up with the weighted average of the site-specific causal effect. Remember that we are maintaining that the RDD continuity restriction holds in each site. Okay. Now compare. It is interesting to compare what happens with the fixed effect estimator to what happens with the NP estimator. The structure of the two estimators is similar. In both cases, what you are doing is taking weighted average across sites. But the key difference is that when you go fixed effect, the weight of each site is the same to the right and to the left of the cutoff. It is Pj. I'll tell you in a moment what Pj is. When you go NP, the weight of the site to the right is different from the weight of the site to the left. This is the reason why the NP might be biased, okay, while the fixed effect is not. So it is clear that if you go fixed effect, what you end up with is a proper causal parameter. It is a weighted average across sites of site-specific causal parameters. Okay.
Enrico, sorry.
Yeah.
Just a question because I got lost.
Yeah.
The first, in equation 16,
yeah.
the first, the terms in square brackets.
Yeah, here.
Why are they different?
Oh, yeah, sorry, that's a typo. This is a minus.
Okay.
This is a minus. Sorry about it. Copy and paste.
Yeah, okay.
Okay, it is plus epsilon minus epsilon. Thanks, Daniel. Okay, so the weight P. The weight P, when you go fixed effect, is here. And the point is that, be careful, this is not a weight proportional to the number of units of the cutoff. Okay, it is a different weight. So this is why if you go fixed effect, even if you end up with a meaningful causal parameter, in general, you do not get the AT&T, nor the ATT. You get something else, not precisely clear what it is. It is a causal parameter. It is not the AT&T nor the ATT. But what you can do is reweighting to end up with the right weight. Okay. The problem of reweighting is that you need to estimate the quantity here to end up with the weight you like. But if you have a small number of applicants in this site, your estimate of this quantity here will be imprecise because the sample size in this site is small. So this way you are adding noise, adding random variability to your estimate. So this is the price you pay to recover the intended causal parameter. A possible way out we propose in the paper is, again, removing units of the cutoff. Okay. Because in that case, Pj is known. It depends only on Kj. So no need here to estimate this quantity here to reweight your estimate. So this way you end up with your AT, just adding a reweighting factor to your estimate. Okay, I'm skipping section 5.1, how to implement the non-parametric version of this fixed effect RDD. Oh, there are some alternative estimators. There are 4 minutes left. Very briefly, the first one is something new to our knowledge. We propose in the paper. We name it double normalizing. So it is here we exploit the analogy to first difference in panel data models. So remember, the NP normalizes the running variable by taking the difference x minus Cj, the value of the running variable minus the value of the cutoff in that site. So the idea here is to do the same with the outcome variable of unexposed individuals. Take a specific unexposed individual inside J, its outcome Yij, and take the difference with respect to the outcome of the exposed individual in that site at the cutoff, the marginal individual at the cutoff. Do that separately in each site. Then what you do, next step is very simple. Pool the samples of these doubly normalized unexposed individuals across sites and run the standard. That's it. The price you pay to implement this double normalization is that exposed individuals other than the one at the cutoff, they do not contribute to this estimator. So essentially you are losing a bit of procedure, which is exactly what we found in our experiments with actual data. The DN estimator performs well. There's no sign of bias, as expected. It is just slightly less precise than the fixed effect, but it's very simple to implement. Rank distance. Okay, so the idea here is from a paper by Abdul Kadiroglu, Engrist, and Patak, elite school in Chicago. What they do in this paper is to use as the running variable the ranks of individuals instead of using the original running variable. And very briefly, the point we make in the paper is that proceeding this way, the order of individuals is preserved within each site. Okay. You're just using a monotonic mapping from the original running variable to the ranks. But when you pull together sites, if the number of individuals varies across sites, this strategy is no longer order preserved, meaning that an individual close to the cutoff in the original metric might end up far away of it in the rank metric. In the case of the paper by Abdul Kadiroglu, Engrist, and Patak, it is presumed, we do not have the data, but presumably this is not a problem because in their case, the size of their groups is is approximately the same. But if there is heterogeneity across sites in the number of applicants, what we show is that small sites groups are penalized by this trend. So they get a weight smaller than the one, maybe much smaller than the one they would get in the original method. The last strategy we found in the paper is by Boas and Hidalgo. What they argue in their paper, this is a paper in political science, what they argue in that paper is that the cutoff relevant for the unexposed individuals is the score of the last exposed individual, while the cutoff relevant for the exposed individuals, the winners, is the score of the first unexposed individual. But this way, proceeding in this way, it is clear that there is no individual exactly at the cutoff. So in a sense, they're getting rid of the problem. But the price they pay is introducing a new problem, because now the cutoff for unexposed and exposed individuals is different, CU, CE. And by definition, CU is larger than CE. This is the score of the first unexposed. This is the score of the last exposed. And I mean, it's very simple to show that if the regression of y0 on the random variable is a non-trivial function of x at the cutoff, then there is a violation of the RDV identifying restriction. The resulting bias goes to 0 when nj, number of applicants per site, is large. But if nj is small, that bias might be non-negligible. Okay, I'm going to the last two slides to summarize. So the starting point is that the RDD is a close parent, a close relative to RCT. This is the strength of the RDD, even if, of course, only locally at the cutoff. And the point is that the analogy between the RDD and the RCT breaks down when we pull together different groups, capital J groups, sites. It breaks down if the following two conditions jointly hold. So first, the probability of exposure at the cutoff varies across groups. And second, this probability is correlated to the site average potential outcomes. Under allocation rule 1, so when you set in advance the cutoff, the first condition, this one, doesn't hold. That is, the problem does not. But when we go with the allocation rule 2, so we set in advance the number of exposed individuals, the problem might arise. Those two conditions might jointly hold. We have reviewed a number of published papers in political economics, political science, and it seems that this setup is quite common. So under allocation rule 2, the procedure to normalize at 0 the random variable and to pool the J groups as if they were a single sample, it might produce a bias estimator for the effect. And there is no theoretical reason to think this bias is negative. So this straightforward solution is to control for group site its effect by adding them to your regression. But take care that in this case, you need to pay a bit of attention to the weight attached to each site to obtain the causal parameter you have in mind. Because otherwise, the default weights might not be the one you need to get the parameter you want. That's it.
Okay, thanks, Enrico. Perfectly on time. So now there is, we have about 10 minutes, even more, for questions. So you should write on YouTube your question, and then it will be transferred to me. In the meantime, people are asking question, Enrico. I have a question.
Yeah.
So everything is, the problem arises when nj is small,
Yeah.
okay?
Exactly.
But how small is small? I mean, is there a sort of rule of thumb, to decide when you have this problem?
No, because the point is that the size of the bias, if we keep units of the cutoff in the sample, the size of the bias depends. It is essentially given by this covariance here. Okay. So you see that here, what matters is the degree of heterogeneity across sites, the standard deviation of the first element of the covariance, the degree of heterogeneity of the sites with respect to the second term here, and then the correlation between the two quantities. So it is not the number nj per se to matter. It is one of the ingredients of the bias, but it is not the only one. Because then, I mean, let me rephrase this sentence. Even with small nj, let's say 10, 20 per site, the bias is 0 in the absence of correlation between these two quantities here. So it is difficult to give, I mean, to me, it is impossible to give a rule of thumb for the bias in terms only of number of applicants per site, because there are other things who matter for the size of this bias.
And the number of sites?
The number of sites is not a problem. It doesn't enter this picture. You might also have a small number of sites, small capital J, but this is not relevant. It is not one of the ingredients I listed before for the size of the bias. Mm-hmm. It is not here.
Yeah. Okay, I don't know if there are questions. I don't see in the chat. No, they are a bit shy. Yeah. Oh, you were too clear, Enrico. So there are no doubts. Okay, Francesco is telling me that there is a problem on YouTube. It's there is a terrible delay. So, but you tried actually this problem also was in the paper, in the original paper on the childcare in Bologna.
Exactly. As I told you, this is a spin-off project of that paper. Yeah.
I see. And the results, if they, and for them, because I don't remember the numerosity, probably since it was concentrated in the area of Bologna, they might have a problem of small number.
I think there is a number in the table here. No, the number of sites was very large.
Ah, yeah.
But there is no number here.
It doesn't mean that NJ is large, no?
No, it is not large. I do not remember the precise figure, but it is not large.
And do the results change? So you tried also to see in some of these papers where you had replication data, how the results change applying, your correction?
Oh, we are working with, in the paper, we are developing an experiment with this paper here, Pop, which is a great paper to simulate what would happen. But in their case, they are lucky because in their case, the number of applicants per site is extremely large. Okay. So
you shouldn't find a difference.
In that paper, it's clear that it is not a major problem. But what we do with their data is to run a kind of mind experiment. What would have happened if the numbers of applicants, instead of being so large, had been, let's say, 1/10 100, and so on. So decreasing the size of their sample to pin down how the bias changes. And we are finding results in line with the theory we are developing in the paper. Okay. So it is a problem. It is a problem when the sample size is small.
Okay. Actually, I don't have question. I don't know, Francesco, if we can stop or we have to wait.
No, we can, I assume, stop. There was a delay with Zoom indeed, and also they told that depending on the browser they were using, there was difference in the volume. So I don't know why this was happening, but we have a question. So I sent to you on this because we are a bit late, and in that sense, that's why the people are slightly behind us.
Okay, so good afternoon. Okay, does similar reasoning apply in a scenario of fuzzy regression discontinuity design?
Yeah, because I mean, I think there is a subsection, a paragraph, I don't remember, an appendix, I don't remember in the paper we are writing. But essentially, the point is the following. If the RDD estimate is the fuzzy RDD estimate, is the ratio of two sharp RDD estimates. The numerator is the sharp RDD in which you regress y, the outcome, on the running variable. The denominator is the sharp RDD in which you regress the treatment status D on the running variable. So essentially what you should do there is to apply the very same line of reasoning both to the numerator and to the denominator of your fuzzy RDD ratio. And it is clear that there is no reason to think that the bias in the numerator and the denominator cancel out. So you don't really need what happens to the overall bias of the ratio. But no reason to think that in that case, the problem vanishes.
Okay, I think we are perfectly on time. I would like to thank Enrico and also the organizer. And
thanks to all of you.
Yeah, and we can stay or move, I don't know exactly, for the coffee break. I don't know if we have to stay, we have to connect on YouTube, right?
No, we stay here.
We stay here, sorry.
We stay here.
Yes.
So other people will come in.
Okay, so we stay here for the coffee, virtual coffee break.
Who is serving the coffee?
Yeah. Okay, thanks.